All right. So while some people are making their way in, hi everyone. Welcome to our next talk here for the fall. And we have Brian Medeiros visiting from the visiting virtually from the National Center for Atmospheric Research. And Brian is a project scientist there at NCAR. He's been there for 15 years. Brian got his bachelor's degree in physics from UC Berkeley in 2000. Then he went on to do his graduate work at UCLA and got his PhD in 2007. And Brian is really interested in clouds and their interactions with global circulation and their role in the climate system and in climate and cloud feedbacks. And he's a key member on so NCAR runs the Community Earth System model, and Brian is a key developer in the atmospheric component of that model, known as CAM, or the Community Atmosphere Model. And Brian is a key developer of that. I met Brian actually. Brian, I don't know if you remember so this is an NSF Science and Technology Center, right? As we all mostly know. There was another one at Colorado State University called CMAP, and I was a graduate student in CMAP, and Brian was, I think, a visiting postdoc. And you
Yeah,
were regularly around the CMAP meetings, and we had a lot of coffee and some discussions many years ago. And then I hadn't seen him for a long time, and now I get to see him again, being part of LEAP. So that's a fun little that's been a fun evolution. So anyway, so Brian today is going to be talking about development activities in the newest version of CAM, and we'll look forward to hearing this. So Brian, with that, take it away.
thanks, Greg. Yeah, this was I was going to try to do an extended metaphor to connect with Leap and do hops, skips, and jumps on our way to developing CAM7. I thought that was especially cute because the buses in Boulder are called hop, skip, and jump. But I won't. I won't. It turns out that's going to be harder to do than I wanted, so I'm not going to try to belabor that metaphor. But I will try to mention some hops, skips, and jumps in our development. What we're going to talk about today is an overview of CESM and development activities around CAM, the Community Atmosphere Model, and what we've been doing going from CAM6 to CAM7 in terms of the actual changes to the model and how we make changes to the model, and then some of associated things around evaluation of the model, and then a little bit about future work with it, with development. So most of this work that I'm going to show is not mine, so I want to acknowledge the entire CAM7 development team, which isn't a huge number of people, but maybe a dozen people or so, maybe a little bit more than that if you include all the software engineers. But especially Julio, Cecile, and Peter, who are the previous co-chair, the AMWG liaison, and the current co-chair of the AMWG, and they do a lot of the coordination of model development activities. And I'll mention a few other specific names as we go along. So LEAP and CESM are pretty closely tied together, and I think we want to bring them even closer together going forward with LEAP's activities in phase two. And so I think many of you will know a lot of the structure of CESM, but I wanted to just review it really quickly to make sure everyone's on the same page. So CESM is a large Earth system model. It has a lot of components that are coupled together. CESM2 is the current version of the model. It was released in 2018. The next version is CESM3. It is going to be released sometime in late this year or early next year. I'm not exactly sure when that will really happen. I mentioned to somebody who works at NVIDIA recently that our development cycle is about 5 or 6 years, and they literally laughed at me, but that's how we work in science. So CESM is this big coupled model, and it has a couple of layers of organization. And one is the code itself. So there's these different components. So SEAM is the coupler that sits in the middle and connects all the different component models, which are shown by these rectangles, by exchanging fluxes. So it takes fluxes from the atmosphere and sends them to the ocean and the land, takes fluxes from them and brings them back to the atmosphere. And then each component model sort of takes care of its own realm of the climate system. So the atmosphere, the land ice, which are ice sheets, sea ice, and ocean. And then associated with some of these models are sort of models that are more tightly coupled to one particular component model. So for example, biogeochemistry in the ocean is really run as part of the ocean model. And the river is really tightly coupled to the land, the river runoff model. Mozart is really tightly coupled to the land model. And there's probably other ones, especially around land, but I just wanted to simplify things for this. And then there's a couple of different configurations that you can run for different component models. So in the atmosphere, we normally are running CAM6, which I'll talk more about in a moment. But there are other flavors of CAM, which have different names. So Wacom and Wacom X are the whole atmosphere model, and so they have a much higher model top. So for studying the stratosphere and the middle atmosphere. CAM-CHEM is the configuration that's run with much more sophisticated chemistry with many more chemical mechanisms involved. So they have their own working groups. So these WGs all around the figure are the working groups, and those are sort of communities of people who work on developing the models or using the model. So the atmospheric model working group is responsible for developing CAM, making decisions about how development proceeds. And there's working groups associated with pretty much all of the component models. And then there are a couple of additional working groups, the Climate Variability and Change Working Group, the Earth System Prediction Working Group, and to some extent the Polar Climate Working Group, which are kind of a step away from development and a little bit more on the application side. They do a lot of community projects, running a lot of production simulations. And then around this whole thing are the kind of governance of CESM. So there's an advisory board and a steering committee. So for the rest of the talk, I just want to focus in on this little piece of CESM, which is CAM, which is an important piece, but in this picture, it looks small. And so CAM6, which was released with CESM2 in 2018, looks sort of like this in kind of a simplified view. So what we do is we solve the equations of motion in the atmosphere using the dynamical core that uses a finite volume method on a nominal 1 degree latitude longitude grid. That's fed into the physics, which is represented by all these symbols on the right side. And they basically feeds through to the deep convection. Then this iteration between CLUB, which is a unified turbulence, shallow convection, and cloud macrophysics scheme, and the aerosol and cloud microphysics. This goes around 3 times to iterate. So basically a smaller time step within the model's physics time step. That's fed into the radiation scheme. And then the fluxes are sent to the surface models. So this is a coupling step where we send all the information to the surface models and get information back. When we get back the fluxes from the surface models, we do aerosol emissions, chemistry, diffusion that's separate from the boundary layer turbulence in CLUB, dry deposition, basically particles falling out of the atmosphere, and various forms of drag, so gravity wave parameterizations and surface drag. And then this goes back around to the dynamics for the next time step. So a couple of things about this is that first, this is a slightly simplified picture, but it has most of the major components. Second is that we use a time splitting technique. So what that means is that each scheme in this picture gets the state that was produced by the last scheme. So and you can think about that as the physics is basically working on the state that the dynamics produces. And that was, you can think of about that as a psi being a temperature or water vapor or whatever at time t. The dynamics works on it, and then the physics works on that to produce the predicted quantity at time t+1. This matters for a number of reasons, but one of them is because that means that you can think of each of the parameterizations as being essentially an operator. So the radiation might be called R, and the boundary layer physics might be called B, and the deep convection might be called Z. Each of those in themselves are nonlinear, which means that the order of operations matters. So when we expand this to show you what the evolution of psi looks like for time t+1, it's really the radiation working on the state produced by the boundary layer physics that was produced by the deep convection, which got its state from the dynamics. And if we change the order of operations, we're going to change the prediction of psi. And we're going to come back to this in a few minutes because it does matter. And it also matters for future CAM development that I'll talk about at the end. So now I want to start thinking about how we're going to change from this structure to update things for CAM7. So the first thing is a jump. So we're jumping from solving the equations of motion using a finite volume approach to a spectral element approach. And this is visually represented here by the different grids. So the finite volume dynamics works on this regular latitude longitude grid that just looks like map grid lines of latitude and longitude. And we're changing to the spectral element, which works on quadrilaterals on this cubed sphere mesh. And you can kind of see the curvature of the mesh shown here. There are a number of reasons for making this change. One of them is highly practical, which is that the finite volume dynamic rapport that we've been using for the last 15 years or so is no longer developed or supported. So we want to move to something that has a little bit more support behind it, interest in it. And along with that comes some additional things, including one is that a deficiency or a drawback of using a regular latitude longitude grid is that the lines of longitude converge. So the meridians converge at the poles. You can see that at the top of this picture. And that means that the grid spacing gets very, very small, which is not good for numerical stability. So in order to take the long time steps we want to take in the model dynamics, we have to do filtering to avoid numerical instabilities near the pole. That's not a desirable numerical approach, so we would like to get away from that. It also introduces other problems that I won't bother talking about. That goes away when we go to this cube sphere mesh. You can see that the grid spacing here is much more homogeneous around the globe. Another thing is the scaling of the numerics of the dynamics here. So the spectral element dicore can scale out to many thousands of processors pretty well. It becomes very efficient. So the bang for your computational buck goes farther with spectral element than finite volume. There is a trade-off there though, because on small numbers of processors, the finite volume core is actually cheaper than spectral element. So there's a crossover point, which probably varies depending on what kind of machine you're using. And the other thing that I wanted to mention about the spectral element dicore is that it allows a new capability in CAM, which is using regionally refined meshes. So you might have this kind of very coarse resolution mesh for most of the globe, but then refine it down to a very high resolution mesh in a particular region of interest. And that's permitted in the spectral element dicore because of the way it's constructed, but it's not possible really with the finite volume dicore. So this produces a new capability. So this is going to be the new dynamics and the grid and horizontal grid for CAM going into CAM7, but we're also changing the vertical levels. So for CAM6, we had a model top around 40 kilometers, and the entire atmosphere was represented by 32 vertical levels, which are the nominal pressures are shown here. And now what we're doing is we're moving to two different vertical grids with CAM7. One is a 58 level vertical grid that has its top also around 40 kilometers. And another, which we're hoping to run for all of our CMIP-like production runs, which is L93, so 93 vertical levels, and its top is around 80 kilometers or so. And you can see that there's approximately evenly spaced levels in the mid-troposphere and into the stratosphere with the L93 grid. And that's in order to better resolve the stratosphere with a version of CAM that's not Wacom. So Wacom has an even higher top and more vertical levels. But we do want to represent vertically propagating waves, and I'll show you why in just a moment. This is just a zoom in on the far right, showing that we're also down here in the boundary layer in the lower troposphere, we're adding 10 additional boundary layer levels in the lowest 3 kilometers or so. And we're lowering the bottom model level from about 50 meters to 17 meters. So this is a big change, and I'll talk about that again in a couple of slides. So first I want to talk about this mid-tropospheric vertical spacing, which is 500 meters. The main reason we're trying to increase the free tropospheric vertical resolution is to resolve vertically propagating waves. For example, equatorial waves that propagate into the stratosphere and provide momentum forcing for the quasi-biennial oscillation, the QBO, which is a source of predictability in the climate system. And so this is just a picture of that. This is ERA5 showing a composite of the QBO. So the westerly phase shown in warm colors and the easterly phase shown in blue colors. And you can see that it forms and it propagates downward toward the troposphere and gets pretty low to almost 100 hectopascal or so. This was not possible to represent in CAM with the 32 levels with the low top. So we raised the top, and then we've done a number of experiments to look at the sensitivity of the QBO to the vertical resolution. So this is a series of simulations with 1,000, 900, 800, so on, meter grid spacing in the free troposphere. And what we're settling on is 500, and we've argued about whether we should go to 600 or 700 or go down to 400. So we compromised, and we're going to 500-meter vertical grid spacing in order to capture the amplitude and the phase of the QBO. And you can see it comes down much lower when we go to 500 meters grid spacing than 1,000. So that's the free troposphere. And then there's also the boundary layer part, which we wanted to increase the vertical resolution in the boundary layer for a number of reasons. One of them is to capture thin cloud layers over the ocean, so stratocumulus and tradewind cumulus, which can have fairly fine vertical structure in the real world. And we think these clouds are important for cloud feedbacks as the climate warms, so we'd like to represent them better. But another reason is to better capture temperature extremes, especially cold extremes over land and ice, where the surface can get very cold, and that leads to a surface-based inversion and a very thin boundary layer. And with a 60 or 50 layer lowest model level and very coarse vertical resolution in the boundary layer in previous versions of CAM, we really could not capture stable boundary layers at all. We're hoping that going to this much higher resolution boundary layer with grid spacings of a few tens of meters stretching up to about 200 meters at 700 hectopascal, that we'll be able to capture stable boundary layers and surface-based inversions much better. But once we introduced this new grid, we found that the tropical deep convection was behaving extremely badly. There was pathological behavior where it destroyed the climate. Looking into it, what it seems to be the main culprit is that the deep convection parameterization, which it's based on Jang-McFarlane. It's a mass flux scheme, and it relies on consuming CAPE that's determined by raising a parcel from a layer in the boundary layer upward to determine how much buoyancy that parcel has and how much CAPE can be consumed. And the properties of that parcel were always previously coming from the level in the boundary layer with the maximum moist static energy. And when we went to this new vertical structure, that level was often one of the very lowest model levels, which are these really thin layers. So we would lift the parcel in the calculation, and it really wouldn't have much CAPE. So the convection was essentially being impeded by not having enough energy available to actually stabilize the atmosphere, which led to bizarre knock-on effects once you start impeding that kind of instability removal. So what Rich Neal has done as a modification is, instead of launching the parcel from the level with the maximum moist static energy, which tends to be near the surface, we're now launching that test parcel from a hypothetical level in the top part of the boundary layer, the subcloud layer, using the vertically integrated moist static energy of a few levels in the boundary layer. So if you're running with coarse resolution, that's probably going to be 1 or 2 levels. But if you're running with this finer vertical resolution, it'll be several levels being averaged together to determine the parcel properties, which I think is consistent with the philosophy that goes along with this mass flux scheme. Doing this is the main, basically got us back to the previous behavior of deep convection. So the climatology looked fairly reasonable. And there are some other changes in the deep convection that are less important, I think, for our purposes here. And then also for CAM7, we have a whole bunch of other updates, which are mostly hops and skips, to go back to our metaphor. So the turbulence scheme club has been updated. It's developed at the University of Wisconsin-Milwaukee by Vince Larson and his group. And so they're continuously updating the scheme, and CAM tries to keep up with it. And we have a couple of collaborative projects that develop that scheme along with them. And so it gets pulled in as an external code repository when you build CAM. Microphysics is similar. So we've been using Morrison-Gettleman version 2 microphysics. That's being updated to PUMAs. This is For a while, it was called Morrison-Gettleman version 3, but they changed the name to PUMAs. But this is an updated version of that microphysics. It has a number of improvements, including improved ice fall speed, fixed number limiter that we'll come back to in a second, and a few other things. It is also now living in its own separate code repository that gets sucked into CAM when you build it. Radiation is another update. So we're transitioning from RRTMG to RRTMGP, which is a more modern code design. It has updated spectroscopy under the hood, which provides a more accurate answer in the radiative transfer calculation. It is also pulled in as an external repository. Aerosols have a slight update from MAM4 to MAM5. That's not a version number, that's actually the number of modes that are being represented. There's also updates to emissions, including a major update to dust emissions that's just coming into the model right now. And optionally, you can use HIMCO emissions, but I don't think that's going to be the default. I don't remember for sure. And then gravity waves have been updated slightly, and surface fluxes are being updated slightly as well. So a whole bunch of smaller changes. And I just wanted to go through a few of these as examples, starting with this ice number limiter, which got a kind of a lot of attention in some circles of the community. So CESM2 is a very high climate sensitivity model. So if you double carbon dioxide and run the coupled system, you get more than a 5-degree warming. And that's outside the likely range of climate sensitivity, and it's been described as one of the hot models in CMIP6. And one of the culprits for that seems to be a change in the Southern Ocean clouds. In particular, in CESM1, which had a climate sensitivity around 4 degrees or so, the Southern Ocean clouds were basically completely ice clouds. And so when you warm the climate, the ice transitions to liquid. That acts as a negative feedback on the climate, slows down the warming, reduces the climate sensitivity. In CESM2, a lot of work went into producing more realistic Southern Ocean clouds that are a mixture of ice and liquids, and that was successful. And so there's less ice to transition to liquid in the base state of the CESM2 climate. So when you go to warm it, there's less negative feedback, which means that the positive feedbacks are more exposed and you get more warming and a higher climate sensitivity. But we got a lot of warming, and people have looked at this Southern Ocean as being a main culprit for our increased climate sensitivity. And when Zhang Zhu in particular ran paleoclimate simulations, he found that the sensitivity going the other direction toward cooling in the last glacial maximum was also too large, way outside of the bounds of paleoclimate proxy records. So as part of retuning the model to capture the last glacial maximum better, they discovered that there was an ice number limiter in the code that hadn't been correctly changed, going from Morrison-Gettleman microphysics version 1 to version 2. Essentially, what the idea is to limit the production of ice particles by making sure you don't produce more ice crystals than you have ice nucleating particles. If the tendency of ice particles is too large and you're going to use up all your ice nucleating particles, then it would cut off the production of ice. In the transition from MG1 to MG2, that limiter wasn't adjusted correctly to account for a new process, and so the limiter was being set way too low, which basically cut the amount of ice down in some circumstances. That's been corrected in PUMAs, which is the update, and now we have a much simpler limiter that happens at the end of the ice physics. Basically says if the ice number is outside the bounds of reality, then just limit it to a particular fixed upper bound. But this limiter has gotten a lot of attention because people have pointed at it as a major flaw in CESM2 that leads to a really high climate sensitivity. We've been recently doing work to investigate this and quantify exactly how much it matters. This is work by Margaret Duffy that's in prep. Turns out that whether you use CESM2 with the ice limiter being incorrect or correct it, CESM2 still looks like CESM2 in transient climate runs. And this is a bit of an aside to everything, but if you look at these colored lines in these graphs for an SSP simulation, 1% CO2 increase simulation for 150 years, and an abrupt 4 times CO2 simulation for 150 years. The colored lines don't look as different from each other as they look from the gray lines in the background. Those are the CMIP6 models. So with or without this ice number limiter, we have a very similar transient climate response, although a different equilibrium climate sensitivity, but we're still, the CSM2 model still looks like the CSM2 model and is well within the range of CMIP6 models. So that's an aside, but we've spent a lot of time thinking about it, so I wanted to make sure to say it. Coming back to CAM7 physics updates. So I wanted to return to this time loop really quickly. So remember, we went from dynamics into the physics, and we went through all these processes. After CSM2 was released, it was a weird oscillation was detected. And you can see an example of that down here from Adam Harrington. So this is the V component of the wind, and you can see these oscillations in the solution. This is a single column model run with different numbers of levels, and that doesn't matter, but you see these weird oscillations. Tracing this into the code, it turns out there was an inconsistency in the near surface physics, which turns out to be because of an offset between where the wind stress is calculated and where it's applied. So the surface stress is essentially calculated at this surface coupling step in the physics. So you can think of that as happening at time t, but that surface stress then doesn't get used until you come all the way around the physics loop, go through the dynamics, come back, and it gets used in club in the boundary layer physics. And that's basically at time t+1. So there's an offset in time between when the surface stress is calculated and when it gets applied. And that caused this kind of like push-pull kind of oscillation in the physics, which doesn't look great when you start to look at individual time steps. So this has been corrected. You can see evidence of that here. The correction is essentially to move this surface coupling up in the time step to right after the deep convection. And so that's been Adam Harrington applied this for CAM7, and it took a tremendous amount of work, because if you remember when I showed you the time splitting approach, where each parameterization gets the state from the previous cross parameterization, that can really affect the solution. So, and the whole code is set up to run in a particular series of processes. And so moving things around was a tedious process, and poor Adam had to do it. And now this is what the time loop looks like for CAM7. So you go from the dynamics, which is changed now, to the spectral element dynamical core, and you go into the deep convection, which is now modified to use the new vertical grid. And then we couple with the surface fluxes. We come out of that and we do our new aerosol emissions and come into this same kind of iteration between the boundary layer scheme and the microphysics. We still iterate that 3 times. These schemes have all been updated. Into the new radiation scheme, RRTMGP, into the updated aerosol chemistry scheme, MAM5, and then into the diffusion, dry deposition, and the modified drag, which is still being modified, which is why I put it hashed. So you can see that from going from CAM6 to CAM7, we have quite a few changes, including the structure of the physics and many updates to individual packages. So I wanted to now spend a couple minutes talking about how we've gotten to that, not just in terms of the actual physics of it, but how we do it as a process. And so this is kind of a different time loop, which starts on Tuesday mornings and goes around to Friday mornings and then repeats. So on Tuesday mornings, the CAM scientists and CAM software engineers get together to go through all of the software engineering tasks for the week. I'll show you an example of that in a minute. And then there's an additional CESM project meeting where we talk about the development of the coupled system. So the CAM scientists get together with the developers from the other component models. At the same time, the CAM software engineering team has a separate meeting to talk about the software engineering details and tasks for the week. And then things go around on Friday morning. The CAM science team, development team gets together to talk about what simulations are looking like and what needs to be done next. And then simulations are run basically over the weekend, and we start the cycle again. During this, as changes come in, changes need to be proposed as a GitHub issue. So GitHub's at the center of this whole thing, and there's lots of interactions around the loop. So discussions happen there about what particular changes are going to mean. A pull request needs to be issued, and that triggers a series of detailed code reviews by the CAM software developers or software engineers. Sometimes, and especially if the pull request is coming from an external group, the CAM scientists will be pulled in to also review the code. Once the PR is accepted, once the pull request is accepted and the code is brought into CAM, it means it's there. A new CAM tag is issued, so a new CAM version, if you will, but that doesn't mean it's part of CAM yet because it still needs to be evaluated for its effects on climate. And it still probably is subject to additional modification and tuning as part of the release process. So that Tuesday morning meeting between the CAM scientists and software engineers looks kind of like going through this. So this is the CAM development board. We talk about all of the CAM tags that have been made in the last week, CAM tags that are coming up this week, and then go through what's happening in terms of like what pull requests are basically ready to go in and become new CAM tags or going through review, what PRs have just started to review, and what pull requests are not yet started, and anything that's coming up. So, and then we talk about a few other software engineering related tasks as needed. The Friday morning meeting is pretty different because it's a lot of talking about individual processes and how they actually manifest in simulations. So this is a lot of informal presentations of work in progress. And these are just figures that have been shown in recent meetings over the last few months that I pulled out of the slide deck that we show every week. There's a lot of updates on the status of simulations, discussion and planning. And these are examples of issues that we've been talking about lately. So we have an East Pacific precipitation bias. We've been going back and forth with the oceanographers to determine whether it's an ocean issue or an atmosphere issue. Turns out it's both. We often are talking about the Labrador Sea freezing in pre-industrial coupled runs, and that's shown down here. You can see this red line popping up. This is an issue that comes up often. We had the same issue with development of CESM1 and CESM2, where the Labrador Sea would suddenly spontaneously freeze, and that becomes an issue because it doesn't unfreeze in most cases in a pre-industrial run. We also have been talking about a stratospheric water vapor bias in CAM, especially with the new L93 level, the 93 level version of the model. We want the stratosphere to look pretty good, so we want the water vapor to be right. This also ties into those changes in the deep convection scheme, which is essentially the source of water for the lower stratosphere. And then in the last couple of weeks, we've been looking at the 20th century simulations in the coupled system, and they're too warm. And I just wanted to show you a couple pictures of this. This is literally from last week and this week. This is the time series of global mean surface temperature through the 20th century. And these colored lines that are too high are the surface temperature anomalies in recent versions of CSM3 or prototype CSM3. And you can see that they all warm too much in the mid 20th century. And this gray shading is the CSM2 large ensemble, and the black line is an observational estimate. We think that this has to do with aerosol cloud interactions. So this is the cloud shortwave cloud radiative effect. And you can see it's not, the colored lines aren't falling off in the mid 20th century the same way that we see in CSM2. But we've been trying to dig into the cloud aerosol microphysics and try to figure out what's going on. So we've been looking at cloud drop number concentrations, which can be high or low. So we kind of think just this week we've been deciding that maybe cloud drop number distributions are a red herring, so we don't really know what's happening here, and it's a problem that we're like desperately trying to solve right now. We'll be talking about it tomorrow at that Friday morning meeting. So we saw here in the development meeting, we see a lot of individual plots from individual people doing investigations, but we also have an automated model evaluation system that we're developing. So on the software side, we have regression tests, but in terms of evaluating the climate, we're developing this AMWG diagnostics framework, or ADF. It's a Python-based package that basically makes a bunch of plots. and spits them out into a website, a static website that looks like this when you land, when you open the homepage, and you can click around and browse through a whole bunch of figures. This is run by basically a user modifying a YAML file to tell the package what variables to plot and what kinds of plots to make. We can have maps and polar plots and zonal means, and this is a QBO plot and Taylor diagrams, and there's several others in the package. And so this is the first line of evaluation. So we run these development simulations. We run the ADF to produce these plots. We click around and look at what's going on to make a first level evaluation. The ADF can actually also run the climate variability diagnostics package, the CVDP, that's developed by Adam Phillips. So those are useful when we want to start to look at modes of variability. And we've recently incorporated, thanks to Danny Coleman at NCAR, the NOAA MDTF package. So this is mostly looking at process-oriented diagnostics, so things related to the MJO or blocking or other extremes. And in addition to the atmospheric side of things, we're developing a new package at NCAR called Cupid, which is a framework for running sets of diagnostics. So the ADF will be one of those, and hopefully when we run coupled simulations, we'll be able to run Cupid. It'll run ADF for the atmosphere, and then it'll run other packages for the other components. And so we'll have one unified place to run all of the kind of routine diagnostics, which we've been lacking up until now. So what we're doing in the current process, and you saw a little bit of that with that 20th century run, was model tuning. And this is just an example of how we do this tuning. So we literally are doing runs that are incremented in number. Yes, it did start at 1. And we go through and we do these evaluations. Some of them are ad hoc, some of them are routine, like running the ADF just to make sure everything looks normal. And then when we have something that we want to make adjustments to, we'll do a new run. And then 104 here is an example where it was the same as run 103, but the club C8 parameter has been adjusted from 4.25 to 4.95. And the description of this is tuning. So this is a very manual process, and it's slow and expensive. And so this is one place where I think work in LEAP can make a direct impact on CAM development. And one idea for this is through perturbed parameter ensembles. So systematically varying the free parameters in the model to try to find optimal parameter settings. We have some experience with this with CAM6. So this is an example from Chuda Eidheimer's paper, looking at a whole bunch of parameters and a bunch of global fields and how the parameters affect the sensitivity of or affect those fields. So the colors show the sensitivity. So immediately, these kinds of perturbed parameter ensembles can provide some useful information by quantifying the parametric sensitivity and informing parameter ranges and indicating which parameters are really useful for tuning, which have high sensitivities or low sensitivities, and for which fields. I think that there's an opportunity here to apply machine learning approaches, doing emulation to optimize parameters in a more automated way. Yang and Greg have already been doing this to some extent with both the NCAR model and the NASA model. But there's a challenge also, which is we don't know what to optimize. And if you optimize one thing, you might be degrading something else. And you get different answers for what parameters are best depending on what target you have. So that's a challenge. And another challenge is being able to do this really fast, because you saw that this is basically, we have a weekly time loop where we want to change the model, run it, and evaluate it. And so we need to be able to do parameter optimization as fast as possible. Otherwise, we're going to resort back to the same thing that we're doing now, which is hand tuning, which is again slow and expensive. So we have a LEAP project, and Adisu and Yang are going to be starting on this in October. And one of the things that I think we can do is to try to develop some workflows to accelerate this model tuning process. I just wanted to spend a couple minutes at the end, and I know we're running out of time probably, talking about what happens when we're done with CESM3 and CAM7. So we're at the point now where the scientific part of CAM7 and CESM3 are about to be finalized. So there's a code freeze coming this month or maybe early next month, where no additional science capabilities are going to be added to the model. That doesn't mean the model's done, because there's still a bunch of software engineering and model tuning that needs to happen over the next few months before we release the model. Once it is released, though, we basically jump into CMIP7. And so these are some pictures from the CMIP7 website. And you can see that if you look at the timeline here, AR7 fast track runs are slated to start in early 2025. That's essentially when we think we're going to be done with CSM3. And so we might be late starting our fast track and deck runs compared to this timeline, but I'm sure other modeling groups will too. But then once we do get started, these are dozens of simulations, thousands of simulated years, tons of output to deal with, and a substantial amount of post-processing to change the CAM and CSM native outputs to the CMIP compliant outputs. So this is a huge undertaking that we're still organizing now. And as soon as we're done with CSM3, there will be additional community projects that people will want to do, including a new large ensemble, single forcing ensembles, and there's a big push to move more strongly into Earth system prediction, doing subseasonal to seasonal prediction and decadal prediction, which requires additional model development and workflow development. And development itself doesn't really stop once we have a final version of CAM7 and CSM3, because there are plans already to bring in additional capabilities, including developing and tuning a high resolution version of the model. That would be like a 25-kilometer atmosphere. So that's going to be a large amount of work just to move to a 25-kilometer version of the atmosphere. And if we want to couple it to a 10-kilometer version of the ocean, that's an additional tuning exercise that needs to be tackled. There's also plans to incorporate machine learning-based parameterizations coming from LEAP and also N-squared lines and other projects into CESM. This work has already started with the warm rain microphysics that we've heard about in LEAP already. And then there's also collaborations to produce ultra high resolution versions of CESM, at least CAM. And so Earthworks and StormSpeed are two of those that are looking to produce different versions of an approximately 3-kilometer global version of CAM, using different dynamical cores, for example. And this is an example of one of those, looking at a 60-kilometer version of CAM, and then a regionally refined version, like I mentioned earlier, where we refine from 60 kilometers down to 3 kilometers in this maritime continent region. And the plot is showing the phase of and amplitude of the diurnal cycle of precipitation. And you can see how, and the observations are on the bottom, you can see even without tuning, just going to much higher resolution produces a much better representation of the diurnal cycle of convection over these islands and around them. So that's also a huge undertaking computationally and in terms of software engineering. And we can't just be thinking about CAM7 and what to do with it, because there's already the beginnings of plans for what to do after CAM7. So we already have to be thinking about the workflow and the development cycle toward CAM8, which, it's overwhelming, but we know we have a few things to do, including deep convection needs to change in CAM8 if we're going to have the capabilities to go to these convection permitting resolutions. We need a scale-aware parameterization. So one project is looking at evolving toward a eddy diffusivity mass flux approach. So that's coupling a mass flux scheme to club. We also need improved and more physically consistent coupling with the ocean. And in particular, there's a new ocean model in CSM3. I haven't even mentioned that, but we're moving from POP2 to MOM6. MOM6 expects to get an enthalpy flux from the atmosphere. So that requires a detailed accounting of the thermodynamics of the atmospheric physics. So Peter Lauritsen has been working on developing code to consistently get an enthalpy flux that matches what's happening in the atmosphere and pass it to the ocean. We are also looking to improve the treatment of subgrid scale heterogeneity as part of the class project, essentially coupling club to the heterogeneity that's in the land surface model. There's going to be changes in the club parameterization, moving from a length scale formulation to a time scale formulation. likely at least. And then at NCAR, there's this SEMA project, which is trying to bring some of the different atmospheric modeling efforts that have been happening at different parts of the organization together. And one of the project within that is converting all of CAM physics to be CCPP compliant. That's a major infrastructure change for how parameterizations in CAM work. It essentially takes out the interface between CAM and the parameterization scheme and replaces it by automatically generating that interface code by reading metadata associated with each parameterization. And then this enables a few things, including being able to reorder the time loop much more easily. So going through the work that Adam did hopefully won't be as onerous in the future because the entire parameterization suite can be reordered by changing what's called a parameterization suite file, which is an XML file, which the CCPP infrastructure reads and then builds that parameterization suite on the fly. Another part of SEMA is integrating impasse into CESM. So that's the model for prediction across scales. That's basically a non-hydrostatic dynamical core on a hexagonal grid that's shown over here into CAM as another option for dynamical core. The major thing here is it's non-hydrostatic, which means it can go to these convection resolving scales that we want to do for ultra high resolution. And in fact, this example from Xingying Wang was using CAM impasse. So that will continue. And then I'm sure there's a zillion other things shown by these dots. So hopefully that wasn't too much and too boring. Thank you very much. And I can talk about any questions or take any comments you have.
Thank you, Brian. Okay, so we'll do questions now. We'll start with some of the early career scientists in the room. Sam, you had your hand up. Did you want to ask? Here, use the mic so they can hear online.
Thanks. Was extremely interested in the diagnostics tool you mentioned. As a software person getting started on making changes to these models, I imagine that's very useful to be able to double check. Um, so it generates a lot of plots right now, which I think is useful, but I'm curious if there's any actual automated testing to like direct your attention to things which are specifically wrong, or you just have to like know what the plots should look like and eyeball them.
Yeah, so the automated testing is all done on the software side, basically to check that the model is running correctly. But then, once we get to the diagnostics, it's really expert assessment. So you have to know what to look for. It would be amazing to actually have something to at least direct attention toward some particular thing. And we've talked about that in terms of there are metrics that we could incorporate and maybe produce some kind of like scorecard that would show if something got much worse or much better. And in fact, the land model uses a package that's developed by DOE called ILAM, which produces a scorecard, which you basically see, I think, like red and green on in a grid for each variable or something. And if it's very red, then you need to go look at it because you got worse. So something like that would be useful, but we haven't had a chance to develop that for the atmosphere diagnostics yet.
Yeah, because it has these like baselines versus the new code. So it seems like you would be able to save a lot of time if you didn't have to eyeball every single one.
Yeah, that's absolutely correct. And we do have the capability of comparing against observations. So if you and doing multiple cases, so we sort of have the infrastructure almost in place to do it, but nobody's actually tackled the problem of producing something like that.
Cool. Thanks.
Okay, other questions.
If anyone has questions online, feel free to use the raise hand function so we can unmute you.
Hi, Brian. This is Marcus.
Hey, Marcus.
So when you're going over like those issues, this looks wrong, this is bad, Southern Ocean, whatever. Um, like how much of those things would you say are definitely like structural issues with code or like bugs, and how many of them are like, oh, we need to tweak these parameters? So I guess what I'm getting at is how many of these things would sort of be addressed by the kind of tuning exercise that might be happening through Leap anyway.
I That's a good question, and it's hard to quantify because we don't keep track uh, in any formal way. So just spitballing it, I would say we have like maybe a maybe a fourth of the things we find, or maybe less at this point. Like, and this changes as through the development cycle, but maybe a fourth of the things we find or less are bugs that are detected, and we trace them, and we're like, oh, well, we just did this wrong, and so we have to fix it structurally. A lot of what we see now is, I would say, associated with the tuning process. So setting parameter values and modifying process rates and interactions between processes to try to optimize the climate. And that we know from the PPE work is ambiguous. I mean, there are different, you could get to the same answer different ways. And so this is another place where like work from Leap could really inform the process, because we basically tune the knob one way. If it goes the right way, then we keep going. But we know that if we tune a different knob, maybe we should have changed the other parameter the opposite direction even.
Thanks, Brian.
Thanks, everyone.